Thank you, Rasmus, for the introduction. Ladies and gentlemen, welcome here to my my doctor thesis defense. I'm very happy to see so many people here, and I'm going to give you a half-hour introduction, if I can, of the research that I've done over the past decade or so, since coming back from my postdoc years in Italy. So basically, what I want to talk about today is nonlinearities with ultrafast femtosecond laser pulses. And so to sort of grasp what we are talking about, I just wanted to show you a nonlinearity that we take somehow for granted every day, namely this green laser pointer here. So if you notice that this green laser pointer here is much bigger than the red laser pointer that I have here in my hand. And this is because it's a much more powerful laser. So it needs more optics and more batteries and stuff inside. But it's also based on infrared laser technology. So basically, the laser that is inside this laser pointer, you cannot see it with your eyes. So it's not really a very good laser pointer for us. So in order for us to really grasp what comes out of this laser, we have to, after the laser crystal, which is here, there is another crystal, which is a quadratic nonlinear crystal called KTP. And KTP is then converting the infrared laser light to the green light that then comes out of this laser pointer through a process called second harmonic generation. So second harmonic generation takes the infrared pump photons, 2 of them, and it converts them to the second harmonic, which is half the wavelength at 532 nanometers, and then we get the green light at this wavelength. For doing this, we need to have phase matching, otherwise the process is not efficient and we don't get any green laser light out. And it turns out that this is exactly the same type of crystal that I have used in my work. I have only done a trick to this crystal. I have removed the phase matching. And then I generate what is called a cascaded nonlinearity. So I sort of misalign the crystal. So it's very inefficient second harmonic that we get out. But instead we get another property out, which is a defocusing nonlinearity. And that is what I have based the research on that is in this thesis. So it's exactly one of these crystals that are inside here that I have actually used to make my discovery. So it goes, this is a nonlinear process. So it goes to tell that nonlinear processes are needed to generate laser light at wavelengths where we normally don't have laser light. So if we could have made a green laser pointer directly, we would have done it, but it's much more efficient to use infrared light and then make the green light. So in our laser lab, unfortunately, for demonstration and so on, our lasers are pretty boring. They are namely infrared lasers. So if you go into our lab and you turn them on, you cannot really see the laser radiation. So in order to see the laser radiation, we do some tricks. So this Lego man here has now a very small light filament in his hand, and this is where we focus the infrared laser light in air, and then we generate this light filament. So suddenly the infrared light becomes visible. So there's white light. You can see here there's a white filament, and then white means that it's all the colors for the visible eye. So suddenly we generate a lot of colors. At the exit of this filament, the Lego man, he's now looking at a lot of colors that are coming out of this nonlinear process. So actually a photo of this filament and the cone of light that comes out of this filament is a really, really beautiful effect that we often demonstrate to our students in the lab. And this is a highly nonlinear process that is going on and generating lots of new colors. So this is the basic principle. You take a very powerful laser and you generate new colors through nonlinear effects. So what is the difference then between the laser light from this laser pointer and the laser light that we have from the ultrafast lasers? So the laser light coming out of this laser pointer is a continuous wave laser. So as a function of time, the power is constant. And that also means that the color that comes out of this laser pointer is green. It's a single color. But if we go to a pulsed laser with very short pulses, then we have a pulse train coming out of the laser. So we have a very short pulse and followed by another short pulse. And because the pulse now is very, very short, it is associated also in wavelength domain by many colors. So we no longer have now a single color, but we have many colors that compose this laser pulse. And then, because the pulse train has a repetition rate, so the delay between them defines a repetition rate, how many pulses we can have per second, and then that gives them some fine lines in the spectrum that we can then use. So why are we really interested in using these ultra-fast lasers? It is about, one of the things is about the fact that the average power of this pulse train is really, really low. It's on the watt level. But the peak power can be much, much higher, as high as terawatts or even petawatts. So we can have a peak power to average power ratio that is as high as 10 to the 18. So we can get staggeringly high peak powers from these ultra-short lasers. The fact that the pulses are really short is important for freezing processes on molecular and atomic scales. And the fact that the short pulses are associated with a broadband spectrum is also useful for many applications, to have many colors in the same laser pulse. We can also play around with the repetition rate. So a high repetition rate is useful, for instance, for telecommunication. You want to send many pulses per second through the fiber, for instance. It can also be very useful to play around the repetition rate to have these very fine comb lines in the spectrum. On the other hand, if you do ultra-fast spectroscopy, is something that we do in our group as well. The low repetition rate is actually beneficial sometimes, because you want the excited state to go down to the ground state again before you do a new experiment. So you don't want too high a repetition rate. And also, if you want to have these really high peak powers, then you cannot have many pulses, and typically you end up with pulses, 1 pulse per second, 1 pulse per minute, 1 pulse per hour, even 1 pulse per day, so that you have an extremely high peak power coming out of the laser. So, just to give some more basic background on ultra-short pulses, typically we talk about an electromagnetic field that has an envelope, the black line, and a carrier wave, the red line. And the carrier wave oscillates with a cosine, and then the carrier frequency omega naught. So the optical cycle of this field is then defined by 2 pi over the frequency, or lambda, the carrier wavelengths, over the vacuum speed of light. So the power is then this envelope here, and because this is a 10-cycle pulse, which is what typically comes out of a laser amplifier, then the power is actually more or less a single color. Let's say it's green, it's greenish all the way through. But if you take a shorter pulse than this, sorry about this. So let's take a 2-cycle pulse. Now we only have 2 full oscillations under the envelope. Now we have 5 times more peak power, and now we suddenly see new colors in the spectrum. We no longer just have green, but we also have other colors. And going then to a single-cycle pulse, where we only have a single oscillation, we have a much higher peak power, 10 times more if we keep the same energy as a pulse that comes out of our amplifier. And now we have a truly broadband pulse in the wavelengths domain, where we have access to many different colors in the same laser pulse. And then we can also play around that the single-cycle pulse, or even the 2-cycle pulse, we can play around the phase, so we can play with cosine and sine pulses and exploit these different properties. So what is this useful for? When the femtosecond laser became really available in the end of the 90s, there was a field called femtosecond chemistry that came up, where they investigated chemical reactions that typically start, you can see them on a 100 femtosecond time scale, where a femtosecond is 10 to the minus 15 seconds. Actually, femto comes from the Danish word femten, meaning 15 in the exponent. So in femtosecond chemistry, you send in a probe, a pump pulse that excites the chemical reaction, and then with a certain delay, you put in a probe pulse that sort of probes what goes on. And if you then scan the delay, then you have an idea about how the chemical reaction occurs. And this was awarded the Nobel Prize in the end of the 90s. If you go to even faster timescales, then you have molecular vibrations. They typically occur, have a typical timescale of around 10 femtoseconds and above. So if you want to resolve these molecular vibrations, if you want to excite and probe them and get the temporal resolution, you should have a very short laser pulse on the order of 10 to 50 femtoseconds. And then these molecular vibrations, different modes, have different vibrational frequencies that you can then study. And finally, I would say the frontier right now in the ultrafast community is to investigate what goes on the electron timescale. So how long does it take an electron to orbit around the atom? For a simple hydrogen atom, it's around 0.1 femtosecond. So if you want to sort of excite this and probe it and study it, you need ultra-short pulses on the sub-femtosecond scale. So actually, the molecular vibrations are now driving a whole community to look for lasers that are really good at investigating these molecular vibrations. And it turns out that the vibrational frequencies, they occur in the mid-infrared, not the near-infrared where we have most of our laser technology, but in the mid-infrared where we basically have no laser technology today. So the challenge is to go from near-infrared lasers to mid-infrared lasers and investigate these chemical vibrations, molecular vibrations. So basically, the lightest atoms, they have vibrational frequencies in the edge of the mid-infrared, close to the near-infrared, around 2.5 to 3 microns. And then the heavier the atoms are in the molecules for the vibrational frequencies, the further out in the mid-infrared you go. So what you typically do in an absorption spectroscopy measurement is that you shine on to the molecules a broadband laser pulse, and then you have some absorption features associated with these molecular vibrations, and then that gives you some dips in the absorption spectrum. So the task of the community over the past 5 to 10 years has been to supply the ultrafast spectroscopy environment with laser technology that has enough power to investigate these molecular vibrations. And then the final thing was the fact that you want to investigate the electron motion on a sub-femtosecond time scale. And it turns out that in order to generate these sub-femtosecond pulses, you use a process called high harmonic generation. So basically, a very strong laser comes in, and then the strong laser field is then tilting the atomic potential, binding the electron, and the electron is now allowed to tunnel out. And then when the electromagnetic field is 0 here, the potential is back to the ground state, and the free electron is now moving away from the ion. But a half cycle later, the potential tilts again due to the negative sign of the electromagnetic field, and it makes the electron recollide with the parent ion. This process then generates extreme UV or even X-ray radiation. And it turns out that there are some characteristic parameters of this process that are very favorable in the mid-infrared. So the tunneling time scales at the wavelength, which is also reflected in the Keldysh parameter, gamma, which is 1 over the wavelength in scaling. So large wavelengths give very small Keldysh parameters, which allows us to enter the tunneling regime. Then the ponderomotive energy that is given to the electron from the laser is scaling with the wavelength squared, and that also gives an increased energy to the extreme UV and X-ray photons that come out of this process. So all this shows that it's much more favorable to use mid-infrared laser pulses to do this compared to near-infrared laser pulses. And this calls for techniques that can give us these bright mid-infrared few cycle pulses. And this was not available when I started this research. So the motivation behind my research has been to generate, find a process that could generate bright few cycle pulses, and I wanted to investigate a solid state and alternative to gas-based pulse compressors. And I wanted also to investigate a technique that could operate not only in the near-infrared but also in the mid-infrared. Along the way, it also became apparent to me that just taking lasers in the near-infrared and generate directly mid-infrared broadband radiation was an important factor in the community. So what I decided to study was these nonlinear crystals, and then use the trick of misaligning them to generate a cascaded nonlinearity that could give me access to a defocusing nonlinearity. The explanation behind this is that the defocusing nonlinearity could avoid the filamentation problems that are commonly associated with solid-state nonlinear optics with high power pulses. So I decided to focus on what is called a soliton, and a soliton is a nonlinear wave. It looks a lot like the linear wave if you just look at it, but it has some unique properties that it's basically dispersion-free that we actually use in the nonlinear processes that we investigate. So there were some open questions, at least at the time when I started this. It was not clear at all how the mathematical modeling of these solitons worked. There was only very crude and basic understanding of nonlinear effects in these crystals, so we had to develop that. We wanted to link what we discovered in the crystals to what we already know from other fibers and waveguides. And basically, when I started this, I had no experimental facilities, and so we had to build up an experimental lab to observe some of these effects. So the starting point of the research was really to understand how can we use these nonlinear crystals for pulse compression. And this technique was actually pioneered by Frank Weiss's group at the end of the 90s, where they took a powerful femtosecond laser and a nonlinear crystal that was misaligned for cascading. And then after that, after getting spectral broadening inside here, then they compressed the pulse in a piece of glass. The important step forward, in my opinion, was when Satoshi Ashihara's group in Tokyo some years later discovered that you could actually avoid this last step and actually just compress the pulse inside the crystal itself through the so-called soliton self-compression effect. And that was what we tagged on to and started to investigate it heavily. So in the beginning, these nonlinear crystals were not very practical because of issues with polarization. But we discovered a new way of doing it that allowed us to go to more practical applications of pulse compression. And then finally, we have also investigated a so-called non-solitonic case of this pulse compressor. So basically, just to show you what the experiment is about, it's basically just having a defocused beam, having the right intensity in this nonlinear crystal, selecting the right crystal and the right crystal length, and then getting a compressed pulse afterwards due to the soliton effect. So this is an experiment where we did it in a lithium niobate crystal, which is one of the most popular and common crystals. And this crystal, after 1 millimeter, we could see a soliton forming, and we could measure it. And the soliton has now compressed the input 50 femtosecond pulse to 16 femtosecond, which is around 3 optical cycles at this wavelength. And then further propagation gave us a very broadband radiation. So this very short pulse has now generated lots of new colors. So this is the input spectrum in the near infrared. And here we see the total output spectrum that also goes into the mid infrared now. So understanding why this happened, we had to do some very advanced numerical simulations, and I would like to say that I think the start of this experiment was in 2009, and this simulation was done for this thesis to get the complete understanding. So it takes time to understand these things and to get it all right. So basically, in the simulations, we can see that the soliton splits up into two, and we generate these mid-infrared so-called resonant radiation waves, and all these things associated with the simulations we then had to dig in and understand. And in order to do that, I have to go back and explain to you just briefly what it is that we really do. So basically, we take the process of second harmonic generation, where we take two photons and generate the second harmonic. And we have the phase mismatch parameter, which gives a very efficient second harmonic, but then we misalign it so that we are in the so-called cascading limit, where the phase mismatch is large. And then we get a Kerr-like nonlinear phase shift. So we have the cascaded nonlinear phase shift and the Kerr effect of that is intrinsic in the crystal. The Kerr effect is always positive. But the interesting thing about the cascaded nonlinearity is that it can become negative or positive or zero. So zero when we have phase matching. And here I plot the nonlinear phase shift as function of phase mismatch. So no nonlinear phase shift when we have a phase matching at zero. But on each side you have three regimes. So you have regime 1 and 3, which is the focusing regime, which is a standard nonlinearity that you see in all materials. You get a positive chirp across the pulse if you shine a femtosecond laser on it, on the crystal. But if we are in regime 2, which is in the defocusing regime, we can actually access a negative nonlinearity, a defocusing nonlinearity that generates a negative chirp. And this is advantageous and actually quite unique for this system that you don't see in other systems. So to sort of model all this, the starting point in the 10 years ago was an extremely basic model, which is basically a textbook model on second harmonic generation in presence of dispersion. And then later on, I had to derive a more advanced model to understand what really goes on. And this advanced model is advanced and complicated even to me. So if I don't look at it after 1 month, I'm saying, did I write this? So basically, suffice to say that when you go to the cascading limit, where you have this misaligned crystal, both of these equations reduce to a very, very important equation, the nonlinear Schrödinger equation. And this is important because this is a quintessential equation for nonlinear optics, where we have a lot of our understanding from. So the basic model just shows that the Kerr nonlinear phase shift is occurring, while the more advanced model we can assign different high order nonlinear terms that come into play when we launch our defocusing soliton. So basically, the idea is now to take the simulation result, think about how the more advanced nonlinear Schrödinger equation looks like, and then decompose each slice here in a so-called spectrogram where you have time and frequency over here, and then progressively slide through the different propagation distances in the crystal, and observe how the nonlinear dynamics evolves as function of propagation distance inside the crystal, and really decompose all these various nonlinear effects and attribute them to different terms in this reduced equation. So it's a lot of work to do this and to really understand what goes on. But here the sort of basic understanding of nonlinear physics, nonlinear optics that comes in through decades of science helps when you have to do this. So basically the underlying thing here, the guy behind it all, if you wish, is a soliton. So if I have to sort of explain you briefly what is really a soliton. As I mentioned, the soliton is special because it's actually it's a solution to the nonlinear Schrödinger equation in presence of self-phase modulation, this nonlinear term, and second order dispersion. Then you get this very nice red curve here, which is a second hyperbolic shape. And it looks a lot like the black one, which is the solution without the nonlinear term. But the important thing about the soliton is that if you plot the dispersion in an omega k space, then the soliton is basically a straight line. It has no dispersion. So if you model this ideal soliton, then you get something like this. So this is wavelength and this is propagation. And in time, you see that the soliton, if launched with very high power, it self-compresses to a very short pulse. And this is what we exploit to get soliton compression. But if you then add higher order dispersion, suddenly you see that the soliton can become phase matched to a point on the other side of the, so for higher frequencies than the soliton. And this phase matching point is important because suddenly this perfect soliton is no longer perfect. It now destabilizes and it sheds light into this resonant radiation in time, and here it's seen in wavelength. So this is a little bit annoying because we love our soliton and we love the fact that it can compress to a very short pulse, but it's actually an effect that is very useful, it turns out. So basically, to understand a little bit what goes on when you go from the focusing and to the defocusing, the nonlinear Schrödinger equation is the same. Basically, you play around with gamma. So the soliton requires that the nonlinearity gamma and the multiplied with the group velocity dispersion parameter k double prime is negative, and that the intensity is high enough to really excite the soliton. So in the focusing case, this happens. This is where gamma is positive, and then we need to pump below the zero dispersion wave frequency here, and then we can phase match towards the blue. So the focusing soliton will always couple into the blue to shorter wavelengths. If we have now flipping the sign of the nonlinearity, then we go to the defocusing case, and now in order to have a soliton, we have to pump above the zero dispersion frequency, and then conversely we convert the resonant radiation to red photons. So we go to the longer to the infrared and potentially into the mid-infrared. So this underlies why this soliton that we generate here in the near infrared, why we pump below the zero dispersion wavelengths, and how come we get this mid-infrared radiation. And notice also that it's not just a small perturbation of the soliton. We actually have a lot of energy in the mid-infrared from this perturbation. So it's a very strong effect that can be used to convert the light to longer wavelengths. So it turns out that this nonlinear Schrödinger equation, you can sort of say that this is not the only nonlinearity that you can have in the nonlinear Schrödinger equation. You can sort of extend it to include also similar nonlinearities based on cubic interaction. So you have third harmonic generation and conjugate self-phase modulation. If you include those, suddenly you get new phase matching points where you can couple from the soliton into the resonant radiation. Sorry. If you do the same for the defocusing case that we have for our crystal, we then have to extend the equation again with the cubic nonlinearity, but we also have to extend it with quadratic nonlinearities. So suddenly we have two new terms here, which is related to sum and difference frequency generation, because we have a crystal with a quadratic nonlinearity. And then suddenly we can get two new phase matching points due to sum frequency generation and difference frequency generation. The important feature of these compared to the standard case of a Kerr medium is that these phase matching points can be tuned through the phase mismatch parameter. So basically now we can write up all the phase matching conditions that we can get from this full nonlinear equation if we generate a defocusing soliton. So let me just try to synthesize a little bit the information for you. Let me start with the self-phase modulation, which is what we saw here in this experiment and simulation where we had this resonant radiation wave here. This process relies, if you go through the equations, it relies on the fact that the soliton photons, they start overlapping here. So the soliton becomes broadband enough to have photons out here, and these photons are then converted to the resonant radiation waves. So in order for this process to happen, the soliton needs to be extremely broadband. Instead, if you take the process like third harmonic generation, you can see that the resonant radiation photons are actually a sum of different soliton photons that have a lower frequency. The main problem to observe this is that the soliton often lies beyond the phase matching point, so you can never see them. In order to see them, you really have to pump deep into the anomalous dispersion regime to actually be able to observe these resonant radiation points. And this is an important message because it actually turns out that we have a similar problem in our quadratic nonlinear crystal. Because we have that the sum and difference frequency generation solitons are either up or down converted, so that for difference frequency generation, the soliton photons are down converted, and for some frequency generation, the soliton photons are up converted. But the phase matching points do not allow for this to happen. They are simply on the wrong side of the soliton photon. So what to do? Fortunately, then, a technique called quasi-phase matching comes to the rescue. So basically, what we can do in our nonlinear crystal is that we can periodically invert the nonlinearity with a certain pitch, Greek capital lambda, and then we can manipulate with the phase matching conditions. This is a very mature technology, which is good, because then we don't have to rely on some very fancy crystal. And you can actually buy these crystals commercially. And typically we buy the fan-out gratings or the multiple grating crystals so we can play around with this polling period. And when we do that, it turns out that the phase matching conditions become altered slightly. And it turns out to be a good thing, because if we don't have quasi-phase matching, we cannot achieve phase matching in the right places. But if we induce a larger and larger quasi-phase matching wave number, then suddenly the phase matching points start to lie at the right places, namely beyond the soliton photon for the sum case and below the soliton photons for the different frequency generation case. And this discovery allowed us to observe this effect for the first time. So basically we can see now that the full spectrum looks like this, where we have the soliton here, and we have the standard self-phase modulation resonant radiation wave here, the same as we saw before. But because now we have manipulated the quasi-phase matching pitch, we can now see two new dispersive waves, resonant radiation waves, here around 5 microns and here around 1 micron. And they are exactly due to this sum and difference frequency generation nonlinearity. And we can track the peaks experimentally and see that they agree extremely well with the theoretical predictions. So this was basically what we did in lithium niobate. We then said, can we do something in other crystals than lithium niobate? And then we made a roadmap study where we investigated a lot of different crystals to see similar effects. And we have here the plotted as function of the pump wavelength and the figure of merit. So beyond 1, we should be in business with generating solitons. So lithium niobate is here, and this is the curve that we have exploited so far. And then we tried to see if there are some other crystals that we could use, and then we focused on this guy here, lithium thioindate, which we could buy commercially from a company in Germany. And we did the experiment here. We needed to pump around 3 microns to see the soliton. And then we see a very nice, strong spectral broadening associated with the soliton forming and the resonant radiation waves. And we do see in the numerical simulation that we have achieved a soliton self-compression, and the formation of the soliton then gives rise to these resonant radiation waves all the way out to 5-6 microns. So it works also in other nonlinear crystals in the mid-IR. So this was just a brief overview of some of the results that I have given, and if I should conclude on this, then I have set up here the challenges that I started with in the beginning of the talk, and on the right-hand side, I have shown you the solutions that we found to solve these challenges. So we were able to generate bright few-cycle pulses by soliton self-compression effect. This could be done even with millijoule-class pulses. And we were doing this in crystals that are short, compact, and solid-state base, an alternative to the gas-based compressors. We made a roadmap of near-IR and mid-IR crystals that could be used. And we also found a way of generating mid-infrared broadband radiation simply by pumping it with a near-infrared laser. Some of the open questions at the time have now been answered. We have a very advanced mathematical model now on what goes on in the crystals. We have now a very solid idea about what we really need to see this in new emerging future crystals. We also saw remarkable similarities with fiber and waveguide nonlinear optics, but we also saw a lot of new things that allowed us to dig into the physics and understand it in a better way. And over the decade, we have then set up a new lab and done numerous experiments that have confirmed our ideas. So, after having written this, one has to ask what is next for my activities here at DTU. And I would say that I would like to continue to work with these nonlinear crystals because I think they have a lot of potential. So this is certainly one work direction. In the crystals, we typically use really large energies, microjoules, millijoules. The other limit is sort of the waveguide stuff, where we use nanojoules or even picojoules of energy. But the physics, the nonlinear optics, all these phenomena, the solitons, the resonant radiation waves, all these things are actually generally described by some of the mathematical modeling and the numerical simulations and all these things. So we can actually still generate a lot of ideas. And our ideas could hold on from a picojoule to a millijoule and even joule scale lasers. So I have a lot of interest in emerging waveguides. For instance, we have some activities on silicon nitride, and also on novel solid core fibers, which I am working with in a current EU project. Of course, the high power stuff here is based on an alternative to gas nonlinear optics, but there is actually a new alternative to standard gas nonlinear optics, which is gas nonlinear optics in a hollow core fiber. And this is sort of an intermediate energy level compared to what you can do in bulk and what you can do in waveguides. So this is a really interesting research field, in my opinion. And you can also take the same hollow core fibers, instead of filling them with gas, you can put liquids in them and get some really nice nonlinear phenomena out of that. And then ultimately, we have the very, very small nanophotonic devices based on, for instance, metals and 2D materials and so on. And the femtosecond nonlinear optics of that is sort of an emerging area that we have to explore further. So that was sort of an overview, and I would like to end up with some acknowledgements on the scientific side. A lot of the work on cascading was done in collaboration with 4 people, I would say. So my colleague Bin Bin, who's sitting down there, he did a lot of the experiments. And I had a very fruitful exchange with Professor Changlong Zheng, who came from Shanghai on a Marie Curie grant, and a couple of good PhD students, Hairun and Singh, who pushed a lot of the later work in that. On the early days, I had a lot of really nice collaborations with my colleague, Ole Bang, here at Photonic. And one of our old friends, Vyacheslav Kolikovsky, understanding how to generate the soliton-based ideas. And it all started actually when I met Frank Weiss from Cornell and his PhD student at the time, Jeff Moses, who's now an associate professor at Cornell. And they convinced me that these cascading ideas were really interesting to pursue. And then I got to talk to other people in the field, like Satoshi Ashihara, explained me what his thoughts were. Professor Roland Schick showed me how wonderful lithium niobate was. And recently I took some of our crystals to Paul Peterson's lab at Cornell, and we tried to do ultra-fast mid-infrared spectroscopy with some of these spectra that comes out of our crystals. And then I also would like to thank my collaborators in Shanghai and in Taiwan for providing samples to the experiments. And of course, in the department, I've had a lot of discussions with some of the sort of senior staff. So I want to mention, of course, my fellow group leader, Peter Jepsen. I share the lab with you, and we have done a lot of work to get this lab up and running and share a lot of love for ultrafast physics. And then lots of discussion with Carsten Rotvit, Jesper Læsgaard, Asger Mortensen, Leif Oxenløv about all sorts of things related to physics and other things. External collaborators, there are probably too many to mention them all, so I will just leave it there and say that I also have generous support from Danish and European funds, so I'm very happy that they allowed me to do this research so I can stand here today. So thank you for your interest.
No unofficial opponents have registered with me. And so we will, as planned, continue with the official opponents. And I'd like to first invite Professor Dimitri Scriabin to the podium.
I just see. Thank you very much, first of all, for inviting me to the defense of this very strong doctoral thesis. And it was very interesting for me to read the thesis. And it was even more interesting for me to follow career path of Morten through coming to the conferences and listening to his very good talks and very good talks from his group and following his papers published in very good journals. And his publications influenced my understanding in this research area as well, and understanding of my colleagues, as I know from the discussions. So I was very impressed with this work. And I'd like to make a couple of highlights from this work, which I particularly enjoyed. And it's bright solitons due to defocusing nonlinearity and soliton compression and non-soliton compression effects in K2 crystals. I should mention as well that Professor Sorensen provided for me and for Professor Gala a very warm reception yesterday. So some of my most difficult questions melted down during the night, so I removed them from the list. But still there will be some pressure, so don't relax too much.
Thanks, Bache.
Okay, and from your permission, then I will start kind of putting some questions. And I will start from, I think, kind of welcoming question. And what, Morten, do you think was the most exciting discovery have you made during this almost a decade of research in this area?
Well, I think that it was the fact that we could use a crystal like lithium niobate instead of the standard crystals that had been used at the time. Because the first experiments done by Frank Weiss's group and Satoshi Ashihara's lab was done in a crystal where you exploited the cross-polarized interaction between the pump and the second harmonic. And that's exactly the same type of crystal that is in the green laser pointer. So you exploit a type 1 or so-called type 1 or type 2 nonlinearity, where the pump and the second harmonic, they don't have the same polarization. And from a practical point of view in the lab, it's super easy to use that crystal, but it was always limited what you could do with it because of for instance, properties like spatial walk-off and other things. So when basically it was me who had this idea to say, okay, why don't we try lithium niobate, where the pump and the second harmonic have the same polarization. And it was an idea that was sort of dead at birth in the sense that it violated every good thing about a good cascading crystal. So that sort of was a breakthrough where you suddenly realized that cascading could work in a completely different system from a quadratic nonlinearity point of view, and trying to understand why it really worked. I just saw it in a simulation and I thought, wow, why does it work so well? There must be some secret behind it, and that was maybe 2008, I think, 7 or 8, and that was sort of where I got a lot of ideas from, and then those ideas are still there in my head and being investigated. So eventually it came up with this, I think, very beautiful experiment where we used a quasi-phase matched lithium niobate to see this mid-infrared new dispersive wave, a resonant radiation wave. That for me was an extremely elegant piece of work, but it was sort of, if you ask me, it is sort of a consequence of the first idea. So that I think is sort of the place where I think it was a milestone.
Mm-hmm. You mentioned cascading nonlinearity, and when I read your thesis, obviously this terminology happens very often, and then there is a terminology which you use as well, which is effective nonlinearity. Yeah. Can you maybe explain what is the difference, or maybe it is the same?
Well, it's because the cascade is sort of a repeated process. That is sort of one nonlinearity taking over to another again, and back and forth. So in the community, it can mean one nonlinearity followed by another. In this case, it's automatic because what the cascade is pointing towards is that the pump is being up converted to the second harmonic, but then the second harmonic is being back converted to the pump because of lack of phase matching. And this happens cyclically over and over again throughout the crystal. So this is the cascade effect. Mm-hmm. When we talk about the effective nonlinearity, we mean that the pump wave, it doesn't really feel that it's generating a lot of second harmonic light. It really just effectively feels a nonlinear phase shift. Mm-hmm. Coming out of this cascade nonlinearity. So if you wish, it's the second harmonic is sort of like a catalyst for this nonlinear phase shift to happen, but the pump doesn't really know that the second harmonic is there somehow, if that makes sense to you. So that's why we, in the community, that was something that was already sort of coined by Frank Weiss's group, the idea about an effective nonlinearity, because that's what the beam effectively sees. Mm-hmm. Mm-hmm. So yeah, that's sort of the origin. But sort of, if you wish, the cascade effect, the cascade nonlinearity results in an effective nonlinearity.
Mm-hmm. Mm-hmm. Okay, very good, thank you. So, sort of nonlinearity is actually what is defining your model equation, right? In particular equation 2.9, so I just made this big envelope, or beyond envelope, right? Equation, right? And so nonlinearity which enters there is a usual kind of, there are several obviously nonlinear contributions, but there is a set of nonlinear contributions which are associated with a chi2 nonlinearity, and there is a set of contributions which is associated with chi3 nonlinearity. And I have a couple of questions about this model, because it seems to me like it's a main model in your equation. And first question is, so this model includes obviously kind of terms which are standard. For example, just chi2 nonlinearity, right? Like A1 squared for second harmonic, right? And A1, A2 term for the...
yes.
Yeah, well, it's not expanded, obviously, it's one amplitude A. But what about, and it includes obviously high order dispersions. What about, for example, quartic nonlinearity? Why do you think you can neglect quartic nonlinearity relative to some other small effects like self-steepening or high order dispersion?
Yeah. So the high order dispersion is of course pretty standard to include, and self-steepening is automatic in the sense that it's a term that you conserve when you derive the model. Basically my answer is this. I believe that there are higher order nonlinearities, quartic and so on, and also for the Chi3 there are Chi5 and Chi7, because basically what these describe is a perturbation expansion of the linear main effect that we see. So we ascribe the material with a susceptibility that gives a linear refractive index, but then we just add more and more polynomial terms to explain this. But the answer is that we don't really know the associated tensor values, so Chi4 and Chi5 and Chi6 and Chi7, we don't know them experimentally. So if we could measure them somehow, we could assess whether or not they would become important. That being said, this equation here is actually giving rise to fourth, fifth, sixth, and seventh harmonic, simply because you have second harmonic generation here, and then that mixes again with the pump to give the third harmonic, and two second harmonic, then give fourth harmonic, and so on. So you have then a chain of nonlinear reactions that actually come directly out of this equation, but you will never see them here in this basic model. So we could go on, and actually I have been involved in a work where we did this, but we did it in gases. So the idea was that in the gas community, they had this idea, okay, why did we stop at Chi3?
Yes.
Why didn't we measure Chi5 and Chi7 and Chi9 and Chi11? And somebody did this. They measured it. And they called it the high order Kerr effect. And then there was a lot of debate on how to interpret these nonlinear terms and so on. So they were measured in a gas. So similar things could be done here. To measure them and to investigate whether they have an influence on the results. So I would say that this model really describes to a large degree all the effects that we see, which is kind of, so it's a model that is extremely accurate in the temporal scale, but considering that we take a bulk nonlinear crystal and we don't model diffraction, we just throw the diffraction term. The diffraction term should be here. It's not there. So it gives us a way of modeling a 3D system in a 1D plane wave approach.
Is it because you don't see filamentation?
Yes. So basically, if we have a beam spot size at the entrance of the crystal that is large enough, we don't focus too tightly, then we can, in a 10 or 15 or 20 millimeter crystal, we can avoid the diffraction properties. So basically we only have linear diffraction, so we just make the Rayleigh length of the beam much longer than the crystal length. That's sort of the rule of thumb we have in the lab. And then those results, they match really, really well with this simple plane wave model that this is. So we don't have to do very complex 3D modeling as you would like to do in a filament, for instance. Yeah.
So do you think, is anything valuable for future research in doing 3D theoretical and experimental studies?
Yes, I think that there are some things to investigate. There is a sort of, in the filament community, they sort of live on doing not a 3D, but like 2D, because they have a radial symmetry usually to at least get rid of one dimension. So they have one more dimension to take care of than what I have. But some of their simulations, they can take months. And this model is actually really, really slow. But let's say that I can get some results in 1 hour to 1 day in this model.
And how long is the crystal?
10, 20 millimeters. So I am fortunate enough that I don't have to model 10 meters of fiber.
Yes.
But this is also because we need here to have a time resolution, which is on the roughly, we have like 20 points in 1 femtosecond in the time grid. So, and this is needed because we want to model the higher harmonics with a good time resolution. So that's sort of the unfortunate side effect of this model, that you have to have a huge precision in time domain, which slows the computer down significantly. So this guy up here gives very rough results, and I can get results in 5 seconds, 10 seconds, while this guy down here takes 5 or 10 hours.
So I have. I will kind of put my questions which related to this model them together. So if you look at this guy down there, at the second line of this long equation, inside the round bracket, there are 3 terms. There are 3 terms. And first 2 terms are somehow symmetric, right? If you look, the first term is modulo A squared A, modulo A squared A star, right? So this prefactor is complex conjugated, one with respect to another. Why there is no A cube star there?
Because that term lives in the negative frequency domain, and it is there, but it's only acting on negative frequencies, and there is this plus down here and here, and this is my next question. What is this plus? In the simulation, or even in the model, you sort of only consider the analytical field that goes from 0 to infinite frequencies.
And how you implement
But the whole envelope is defined from negative to positive frequencies, and the way to understand this is that at negative frequencies, they are not unphysical, it's just where the complex conjugate equation lives. So if you set up a similar equation, instead of solving the propagation of A, you solve the propagation of A star, so the complex conjugate. You get exactly the same equation, everything is complex conjugate. So there you would have A star cubed, but you need, and you will also have it A star squared here instead of A squared.
How is it decided that A cube star lives in the negative frequency and modulus A squared A star doesn't live in the negative frequency? I would say that they all live across the 0 in negative and positive frequency. So why you are still discriminating? What is your criterion?
Well, it's related to the way that the envelope is defined from the real electromagnetic fields. So some of that theory relies on some work done by Matteo Conforti, and so it was based on these equations that I proposed this model. So basically, it is a way of telling where is how do you get from this envelope A, which sort of spans from minus omega to plus omega, so the whole frequency range from negative to positive frequencies, even if negative frequencies in a physical sense they don't really make sense, but in a mathematical sense the envelope is defined in this way. But then when you have to connect to the real electromagnetic fields, then it is intuitively it's a little bit like when you set up the real electromagnetic field from Maxwell's equations, and then you say that it's composed of the field plus its complex conjugate, and then this is a way to mathematically describe the real field as a complex quantity. So basically, going through the math for that, then you can see that the A star cubed will not give any contributions to here, because you could include it, but every time you sort of cut off the negative frequencies here, then the terms that it gives rise to will then disappear. And yeah.
Okay. Okay. So another thing I wanted to ask about the modeling is about the Raman term.
Yes.
I'm very familiar myself with the Raman in glass, right, and optical fibers. But what is maybe special features of Raman in lithium niobate? What is FR, for example? What is the value for FR?
Oh, that is a good question.
Was it measured or it's empirical?
So it was something that we spent an incredible amount of effort to understand, and basically, if you go through early papers on lithium niobate back from the 60s even, so lithium niobate was one of the first crystals that were produced to do nonlinear optics from lasers. And so it was studied very early on. And if you go through that literature and trying to dig out the Raman fraction, you get very high values, something like 80 or 90%. So it seems that the Raman fraction in those crystals that they investigated then, the Raman effect was really, really strong. Going through those papers, I didn't really get a good match with what we saw in the experiments. So basically, I treated it as a free parameter in many of my simulations, and this was actually a rather painful process, because I had to do, every time we came back from the lab and I had to do some new simulations to understand what we actually observed, I had to sort of sweep this Raman fraction. And right now we are at around 30 to 40% of the nonlinearities related to Raman effects. But it has taken us...
So it's quite a lot. Yeah.
It's quite high, but it's much slower than the literature says.
Right.
So there is something that we are missing. So I suppose that the literature is measuring either on some crystals that are different from ours, or the fact that you use femtosecond compared to the longer pulses they used matters. We don't know. So I have a collaboration with Roland Schick about this, and he has promised me to do some new experiments soon to investigate this, because it is a really important feature to know. It is extremely crucial in the simulations that we know this number. Much more crucial than in nonlinear fiber optics, for instance. If you misalign the Raman fraction a little bit, or if you take the nonlinearity, the Chi3 nonlinearity in a fiber a little bit too high, you just add some more peak power and you survive. And you see a little bit more redshifted soliton or whatever. But here, this is a competing nonlinearity to the effective cascading effect.
That's right.
So having a Raman fraction of 10% versus 30% versus 50% changes everything. So it is a showstopper if to know the Raman effect. And in that connection, I can also mention that other crystals that we use, like the LIS, the lithium thionate for the mid-IR, and BBO for the near-IR, they seem to be much less Raman active than lithium niobate. So BBO, we never use Raman to model this, and we get almost 100% match between the simulation and the experiments. Getting the number of the Raman fraction down and using this model allowed us at the end, actually basically when I wrote the thesis, to get a good match between the numerical simulations and the experiments that we did. We might do some experiments tomorrow that suddenly throw off throw us off course in that direction, because it is a best guess what it should be.
But what is so this is about the relative contribution of Raman into, say, relative kernel linearity.
Yeah.
But what is the frequency of the Raman peak, and what is the width of the peak?
That is well known. So whenever you do Raman measurements of lithium niobate, you always get the same peaks out, and they are much more narrow in frequency compared to glass. And that's because glass is amorphous, and this is a crystal, so it's normal that the phonon modes that are behind the Raman effect, that they actually have a longer lifetime. So so we know this function very well, the HR. It's more like what is its strength, and then this function HR then also changes with composition. So depending on whether you choose one lithium niobate crystal compared to another, then you have the Raman modes shifting around. But we know this pretty much.
So in glass, the Raman peak is about 12 terahertz.
Yeah.
And what is it here, the Raman shift?
Sorry?
Typical value of the Raman shift here in lithium niobate?
It's 7 terahertz.
7?
Yeah, the first one. And then you have a couple of others that are not so dominating. Basically, the higher frequency modes are only getting excited when you have a really short pulse, because then you have the bandwidth to cover these modes. But initially, it's the lowest mode that gets excited, and so around if you have a 200-300 femtosecond pulse, then you start exciting these Raman modes directly when you pump the crystals. And then, of course, if you generate a really short soliton, then you get the Raman modes in play no matter what you do, because the solitons are typically 10-20 femtoseconds, and then there's enough bandwidth to excite all the Raman modes in the crystal. So alone that, I mean, it was my idea to use lithium niobate, so it's my fault that we need to use Raman somehow. But because BBO, you don't need Raman, so it's also probably lies on my shoulders to figure out how this works. So I have taken that task upon me and tried to. There is a good number of man hours in that term, I would say.
Okay. So another modeling, well, maybe not so, a little bit less modeling question which I had was about, you showed in your slides and you mentioned it in your thesis several times, carrier envelope offset, right?
Yeah.
I wonder, is it important for any of your results or for any of the experiments?
No,
it's just contextual.
No, in the sense that I have not. So the pulses that we can generate with the solitons are short enough so that carrier envelope phase shifts become important. So had we had a laser with a fixed carrier envelope phase, then we could sort of investigate by changing the phase and then see what would happen. So we don't have that, but we don't really need it for the different types of experiments that we do. But the process itself should conserve the carrier envelope phase. So once you have a carrier envelope phase stable laser, then you can do the soliton self-compression and get a short pulse out that is where you can trust the CEP phase.
Okay, very good. So I learned yesterday that you did PhD in Department of Mathematics.
Yes.
How did it happen? Tell us a story. How did you develop experimental research program now?
Well, I have good people in my group.
Yes.
So basically, I'm a nonlinear scientist at heart, and it was sort of a chance that I came, a coincidence if you wish, that I came to nonlinear optics. But that was in my PhD, and I never looked back, I would have to say. So that being said, I believe that mathematical modeling and the nonlinear physics and the studies of this is extremely generic to not only optics but to a lot of different scientific branches. And as a nonlinear scientist, one is extremely flexible in that sense, that we are not just dug into a very tiny subspace of probably we can see the same things happening in lots of different places. So basically, the story behind me and the lab is that I was actually supposed to be an experimentalist, but then our laser broke down in my PhD, and then I was supposed to go to the States and do experiment, and then that laser broke down. So then at the end of the day, I came actually to a postdoc in Italy where they have really good experimental facilities. But I came into the theoretical part of that sort of. There were two groups that were collaborating. So it's sort of, I don't mind doing theory and simulations anyway, and I probably don't even have the patience to do experiments. I don't know. but I think that's just having the stable infrastructure that we have at our department and having good collaborators locally and externally, where we have the ability to train PhD students to do the experiments, that turned out to be a really good way of moving the science ahead. So basically, I'm not in the lab, and people get scared when they see me in the lab. But yeah, it's more or less a coincidence, I would say.
Have your group created any IPR based on this research?
Yes. So basically, let's see. This guy down here, there is a patent on that. But it was a little bit tricky to sell it, the idea, because the idea is that this is an alternative, solid-state alternative to gas-based compressors that you can buy today, and that not only you can buy, but that you also use in advanced research labs on a daily basis. Here you use a short nonlinear crystal, and you can scale it up to really high energies. And it's just that the market for that is tiny. So I talked to some companies, and they were not really interested. So there is a patent, but the patent is open now, so it's not protected anymore.
I see.
And then I have another patent on the hollow core fibers. But that patent died a little bit early on because happenstance. It turned out that there was a competing group in the UK, so Francesco Paletti. He wrote a similar patent at the same time, and he submitted it a couple of months before us. So when that was sort of open up, and we were in the discovery phase, the patent died. So yeah, I had spent some time writing patents and stuff. So it's interesting, but it's a little bit frustrating to get to the threshold where you can actually sell the idea and get some useful things out of it.
So how does this collaboration inside ITN is working out on the industry side? Do you have a lot of connections with companies and?
Yeah. So you're talking about the European project that I'm coordinating.
If it has any impact on this, maybe it doesn't. But.
Well, the idea behind in this European project, what we are trying to do is to take this really broadband laser pulses. So they are called supercontinuum. Of course you know, but I'm just telling for the audience. These supercontinuum lasers are sort of, they have been there for a number of years now, and so the science has now become mature enough to go into the industry. So we are trying to explore new possibilities of turning the science into applications. So we are mixing in that project, we are mixing some basic science nonlinear science discoveries, you know, curiosity-driven ideas, and then some companies that sort of give us some ideas about what we can do. Where should we go before this becomes interesting enough for the company to actually consider making it? And one of the interesting things about that project for me is that the femtosecond laser technology has for a long time been a very, very exciting technology for us that work in basic science. But taking this laser technology into the market has not been easy. So recently the fiber lasers have now provided some very, very compact and stable platform for industrial use. So the question is, when does the femtosecond fiber laser become attractive enough to sell thousands of units to some industrial customer? And this is one of the things that we are exploring in this ITN project, this European project. How can we take the really exciting femtosecond laser technology on a fiber-based platform and use it for something that the companies find relevant? Surprisingly, it's not super clear what you get out of using femtosecond compared to picosecond or nanosecond lasers. And so we're taking on that task.
I see. Very interesting. So now question a little bit on blue sky research and on your kind of background in general nonlinear science. So don't you think that this kind of research area redefines a little bit concept of a soliton? I mean, do we still need to call these pulses solitons? Or they already not so much solitons? So where do you start in this well-known kind of debate?
So my take on that is that for me the soliton is a wave that behaves well. Basically, if you take a system and you can find a stable solution in presence of a nonlinear effect, then it's in some way, shape, or form is a soliton. Maybe not in the original sense, but in any practical sense, it's a soliton. And it can then be a dissipative soliton or a conservative soliton or whatever you want to call it. And some of the solitons are not that pure compared to the original soliton from the nonlinear Schrödinger equation. Some people only consider a 3D light bullet a soliton, and if you have the solitons that I show, a temporal soliton, they are laughing because there is no spatial confinement. It will diffract, so it's not a soliton. So this debate is a very heated debate if you talk to the wrong people. But basically, in my work, the soliton is basically a wave that does not disperse. And that's the key thing to understand all the physics behind this complex nonlinear effects. And a key thing that I think that a lot of people in the community had forgotten, they just calculated the phase matching points without even thinking about where they came from. And in that connection, I think it's also worth to mention that when we don't have a soliton and we have so we are in the wrong dispersion case, so we have optical wave breaking. So then there is a shock front coming from the optical wave breaking. And this shock front can also give rise to resonant radiation. And it is not super clear to me why that is the case, because it's not really a soliton in the sense that it's a stable wave that propagates without dispersion, because I think the shock front has some kind of dispersion. But I don't know, because I don't really know how to model it. And I talk to a lot of people, and it's not super clear how that phase matching process works. And I think that's one of the things that I would like to investigate in the coming year or two, is because we have a lot of shock fronts in our system. Our system is fantastic at making shock fronts. And the reason is that the cascaded nonlinearity gives a lot of self-steepening. Right. So it really is a dramatic increase in the self-steepening effect in the system. So it is some of the simulations I have done for different parameter spaces. I have seen really strong shock transformation that I would like to see in the experiment and see if they match, and then try to make a sort of soliton-based model. Maybe it should be a kink anti-kink kind of soliton that could sort of explain why you couple into a resonant wave. I don't know, but maybe we can discuss this afterwards.
Yeah, very interesting. Yeah, sure.
Because I know that this is one of your expertise.
I'm writing my own papers straight away.
Yeah. So.
Yes, and my next question, perhaps you partly answered it, but maybe not right now when you've been talking about shock waves, because in your thesis you're mentioning about, not mentioning, but exploring a lot conventional resonant radiation emitted by bright solitons.
Yeah.
Right, and then you are talking about a radiation, resonant radiation, which happens without solitons as well,
yeah.
Right? I don't remember exactly how do you call it, but this radiation which happens without the solitons, do you really mean, or somehow implicitly or not very implicitly assume that it happens due to shocks, or this is something else?
No, this is something else. It's related to standard phase matching.
Standard phase matching.
Yeah. So it's basically any pulse, if you have enough bandwidth in the pulse, and you don't have phase matching right at the center of the pulse, center wavelength, there might be a sideband that is phase matched. And that for that effect to happen, you don't need a soliton. That is just phase matching between two colors in the beam.
What?
Two colors. So you are in a sideband color of the laser pulse. So it's maybe it has like 30 or 40 nanometers of bandwidth, and you don't have phase matching right at the pump wavelength, but you have phase matching on sideband. You can then calculate this. If I'm close to phase matching but a little bit off, let's say second harmonic generation, which sideband will find its second harmonic? And that is something that you can easily calculate, and that's why we did one experiment that I didn't show in the slides, but where we had an argument with the referee that told us that what we observed was not related to any soliton dynamics. It was just phase match sidebands, and then we wanted to prove the referee wrong. So we did a whole new experiment to do that, and wrote a whole new paper just because of one angry referee. And there it sort of dawned on us that yes, you can have phase matching if you don't have a soliton. Of course you can, but what is it really that the soliton does for us? It's providing this dispersionless feature that gives a different phase matching point compared to a wave which is not.
That's what I want to clarify. So when you have a soliton, you have geometrically you have a kind of intersection between this curve corresponding to the dispersive waves and the straight line. Okay, so when you are talking about this phase matching without solitons, how do you define it geometrically? Is it intersection between what?
Yes, so imagine that you are, if you take second harmonic generation, right? Then if you are close to phase matching of the second harmonic, but a little bit off, then there is no phase matching between the pump and the second harmonic, but there is another frequency that has phase matching then. So just moving a little bit away. So progressively you move further and further away, and suddenly the phase matching point becomes beyond the bandwidth of the pump, and you don't see anything anymore.
Yes. Okay.
So actually, in some cases, the two phase matching points, the soliton one and the non-solitonic one, they are the same. So it's actually very often tricky to see the difference between the two. So that was also a sort of a message in the experiment we did. We found the right conditions where we could clearly distinguish between the soliton-based and the non-soliton-based phase matching points.
Okay, yes, that's very clear. In fiber, right? we observed a lot of back action of radiation on solitons. Do you see any back action effects in these studies? Because I haven't seen that you discussed it much in your thesis.
You mean like spectral recoil and stuff?
Like spectral recoil.
Yeah, sure. So, yeah, for instance, this simulation here, actually, the soliton redshifts very rapidly, and then it meets the zero dispersion wavelength, and then it stops. So the soliton ends up here. So
it's the same.
It also recoils a little bit back.
Yes. Okay.
It's not easy to see on this one, but if you
it's clear,
if you maybe if we're lucky we can see it here in this one here. So the soliton is here and here and here, and you can see this soliton here is initially way up here, and then the Raman effect pushes it close to the zero dispersion frequency. But yeah, it's not easy to see that it sort of recoils, but it tends to do that along the lines with what you investigated also in nonlinear fiber optics.
Can you maybe clarify what is Raman focusing and Raman wave?
Yes, this took us a long time to understand. So it was really annoying to us that we had this side here. We wanted a perfect, very nice compressed pulse, and we didn't want this small blip here. And it turns out that it's because of the competing Raman effect. So the Raman effect, it acts with a delay. So on the leading edge of the pulse, there is no Raman. The Raman is only on the trailing edge of the pulse. So the leading edge has self-phase modulation due to the defocusing effect, but the strong Raman effect flips the sign of the nonlinearity on the trailing pulse. So it actually is a focusing nonlinearity. So it dominates here. But then the Raman is progressively shifted to later and later. So here now suddenly the focusing effect is reversed, and you then generate another soliton. So we call it a Raman splitting of the soliton. And it's only something that I realized when I wrote this thesis and did these simulations. So it's not in any of our papers. This is sort of a consequence of the Raman effect only acting on the trailing edge and not the leading edge of the pulse. And the fact that the Raman effect has the opposite sign as an overall defocusing nonlinearity. So in a standard fiber, the Raman effect and the nonlinearity have the same sign. So you will never see this. But we have seen it in a hollow core fiber, because there you have a similar effect with a focusing nonlinearity and the leading edge, but a plasma-induced defocusing nonlinearity that only acts on the trailing edge, and there we see exactly the same things. So that was where I got the idea from. So.
I see. Very good. Very interesting. So, and my last question about negative frequency. There is a lot of discussion about these negative frequencies, and obviously there are observations as well. Did you see any evidence of negative frequencies in your experiment, so that you need to account in the modeling, right?
No, we could not see that. It was phase matched in a position where it was impossible to see it, because that's also one of the points about the work, is that in order to, you mean the conjugate self-phase?
Yes.
In order to see that, you need that the pump photons, so the soliton photons, are overlapping with the phase matching points. And the phase matching points were always well into the visible, so we could never see them. And that's also why a lot of these experiments, where they see it in a fiber or glasses or whatever they have, they make sure that the phase matching condition is not super far away from the driver wave, and they always try to generate a strong soliton or strong shock front to see them. So a lot of the basic principles about observing that is to have enough photons at the resonant phase matching point. And we never had that possibility.
This series of papers by Professor Trilla on negative frequency in K2, was it only modeling, or they did some experiments as well?
I think it's mostly. I think it's modeling. Yeah, it's modeling. And I know about this work, and we tried to do some work on it as well, and we couldn't find it. Right. They found a super weird phase matching condition where they could see it, and even then they had to spend a lot of time looking for it. And so it was a very painstaking process for them to actually find a single simulation that actually showed the effect. But it was important to show the generality of the effect. Also in nonlinear crystals, but basically they pump in the anomalous dispersion regime, and they are in the regime 3 which means that they have a focusing cascaded nonlinearity. Right. So experimentally, tricky to observe because you will have a filamentation. But maybe the filamentation can be controlled and you can see it. So then we would have our colleagues in Lithuania, Audrius Dubietis, to do this experiment, because he's doing that right now, basically. So filamentation in BBO crystals. Right. So.
Very interesting. Well, thank you very much, Morten. I think you answered all my questions comprehensively.
Thank you.
And clarified a lot for me. And I finished my line of questioning.
So thank you, Professor Scriabin. A round of applause perhaps already at this time. And then I'd like to invite Professor Katja Gallo to the podium to continue the discussion with the doctoral candidate.
For symmetry, I don't know. Does it work? I thought I will stand. Yeah, okay. So I wanted to start, to add on what already Dimitri said, which I fully subscribe. I want to add words of admiration to the amount of work and also for that effort of bridging theory to experiments. And that we've seen, probably doesn't necessarily come out from here how much work there is behind that to make the bridge between actually even the language and all what is in that equation and what is actually what matters in experiments, how you make it work. So that's actually what is, I think, the most admirable effort in all these 10 years of work to start with the idea and pursue it to the very end, to see it in the lab, to even discover or tell things to experimentalists that they didn't think of, or mistakes they made, like with the BBO, etc. This is really a great effort, and we are all, both from the theory but from the experiment side, also very grateful for. And I'm also very grateful for a very pleasant reading, because you feel when you read also the passion, the involvement, the determination not to give up in running simulations until you get that fitting parameter for the Raman, and checking with everyone also, because that's also what's creating and enabling us to progress both on the experiment and the theory. Some of the questions Dimitri touched upon, but I think I have, because it was so rich, I have a few more. And I will go more on the application and maybe experimental side. And you can expect something on QPM from me too. Now, let's start from the application, which is something that Dimitri already touched upon, and that you also started putting in your perspective and the vision for the 10 years to come, probably. You mentioned also that you're doing experiments with Cornell. So my question or curiosity is, what are the goals that you set for yourself in terms of application now after this 10 years of understanding, where you start with one goal and then you discover other things along the way?
Yes, certainly. I think that that there is a sort of maturity in the community that all these ideas that we have about the just understanding how the soliton works and how it couples, and the nonlinear physics and optics, and actually using that for something this has been paved way by the supercontinuum sources that now are commercially available. And there are a couple of communities now that are trying to exploit this further. So there is in terms of integrated photonics, where you try to take the silicon wafers that we use for computer chips and try to do optics on that, that there's a lot of nonlinear physics there that is very, very similar to the things that I have been studying, and that the whole community has been doing for decades now. And since there are billions and billions of dollars in this community to set up the fabrication of semiconductor based chip, and going into an optics world on that, then that could be a breakthrough of a lot of these nonlinear ideas that could be used there. So a lot of these ideas behind the continuum generation and so on can be used for various types of telecommunication, and you can also make very compact sources that can be used for spectroscopy, for instance, and also related to that, the frequency comb alone, it has already received 1 Nobel Prize. What is that, 13 years ago now? And that I think is an example where we can see some really breakthroughs in terms of applications. For instance, in the mid-infrared, for instance, detection of chemical components in the air where you stand, so they can become so compact that you can fit them on a handheld device in the future, as I see it, so that the pump laser that drives the process is electrically driven and goes into the waveguide, and then you get a frequency comb out that you can then shine into the air and see if you have pollutants in the air, and you get a direct result. I mean, it sounds weird right now, but maybe something like that will be, because I think that our world will look for solutions like that, where you actually use the laser in a much more daily life scenario, not just in the supermarket for scanning the barcodes or other places, but where you actually use it integrated on smartphones or something like that. And it will definitely push for instance, food technologies to new levels, where you don't really need it as a handheld device, but where you rely on the precision and the accuracy and the fact that you can sort of detect things that you couldn't detect yesterday with these new sources, because the laser technology is going further and further. This I see as one of the really big applications of these nonlinear scientific disciplines.
And you're already contributing to that, although it's not in the thesis about your results on supercontinuum in silicon
This
nitride.
is a very particular system where we have a quadratic nonlinearity.
Yeah.
But I think that quadratic nonlinearity is something that honestly is lacking in other systems. I think a lot of these emerging waveguides that you get in silicon photonics, they are really waking up and saying, okay, if we have a quadratic nonlinearity, we can do so much more with our ideas, where we are going. So they're looking for ways to making these waveguides that they have respond in a way so that they have a quadratic nonlinearity, and trying to exploit that. And then a lot of these ideas that is really integrated in my work here becomes directly applied to those ideas.
Yes. And actually, this links to one other aspect that I also have among my questions, or like discussion, dialogue, I would say more. It links again to something which was pointed out by Dimitri about spatial effects and whether you are considering to expand your model to include also the spatial dimensions. If I remember correctly, also in your lithium tile late experiments, then you mention some effects which suggest the presence of diffraction. And can that be one? I know that in simulations is adding complexity and time, but do you think there can be something that can be done in that side, on that side, and also to play, for example, also to use the nonlinearities which are not defocusing and play with that dimension together? So is it
well,
worth?
I think that there is some effort right now in investigating the collapse of the beam into a filament in these crystals, and then again playing around with the fact that you don't just have cubic nonlinearities but also quadratic nonlinearities, gives some new aspects. So that is one case where the spatial dimension becomes important, obviously. But if you want to play around and really generate a sort of stable light pulse that does not collapse into a filament, then we are into the whole light bullet idea. And I think that community is still alive, I would say, but it is not easy to find the right conditions where this would happen. And I think that there is more to be gained if you either just live with a filament and exploit it the best way you can, or you sort of try to avoid it. But maybe there is something there to investigate for sure.
And is that something that you were hinting about when you mentioned these BBO experiments and the fact that there is still not explanation, the last one by Dubietis, where still there is something else which might be interesting happening in even with the focusing regime?
Yeah, I mean, yes, definitely. So they pump at much higher wavelengths than what we did to achieve. They want to exploit focusing, and they want the cascading effect to actually add to the focusing. And then they exploit that, and that I think there are a wonderful set of experiments that they're doing right now, and there is a lot of intriguing ideas there that I think can be interesting to pursue further. Definitely.
One other really beautiful graph, even if it's just one picture, I think there you can just think of all the work which is behind, is that your graph on the figure of merit about the cascading versus care and to effects. And that's really, as you call it, a roadmap and a work which is quite unique, because no one really took the time, the effort to go and look behind in detail in all these aspects. And this led indeed to experiments which no one thought of, crystals that probably were never used or cut the way you wanted them. On that diagram now, you have explored thoroughly lithium niobate, also starting the lithium thiolate. There are many more. Do you see any front runner or someone where you would like to do really your next experiment?
Well, I think that one of the crystals that the community has been very excited about is this one up here. Of course, in my plot, it has the highest figure of merit of all, so I would also be very interested in that crystal, and it's used extensively right now for mid-infrared optical parametric oscillators. But it's a little bit a tricky crystal to get your hands on. It's developed by the American Defense, for mid-infrared laser applications for the military. So it has been classified. So alone the fact that it exists in Europe is a violation of American law. So they are actually trying to track down who has this crystal, and nobody knows anything, of course. But now they have declassified it because I don't think they got what they wanted from it. So maybe there will be some chances now. But zinc telluride is a very typical crystal used for terahertz applications. So it's the good thing about it is it's very high quality, very easy to get, very large aperture and everything. So these are this one as well is a very common crystal used now also in OPOs and different types of nonlinear optics in the mid-IR. So these could be interesting crystals to investigate.
And now the question comes, it's a beautiful graph because also you have the pump wavelength, then you start thinking the sources and how much the development, what you can do and what you can think of doing is actually related to sources available or new developments which are coming. So what are your thoughts in that direction, for example, to work with the selenides, which pumps
so basically there are some groups now that are developing the 7-micron laser. So none of these crystals can be used for the soliton effect, but they can be used in the non-soliton two-step compressor that I wrote this patent on. So the idea would be to try to get enough self-phase modulation and then compress it externally afterwards. And then I always wanted to try to see if there was something you could do around 10 microns with the CO2 laser. But CO2 lasers are they have something like 100 cycles, pulses. So it's very, very difficult to do pulse compression in crystals with so many cycles in one pulse envelope. So then you would need to do a 2 or 3 stage compressor, and then we are suddenly thinking complexities and stuff like that. But yeah, basically there are some movements in this region here where you can get 7-8 micron lasers operating that have gigawatts of peak power already. That would be interesting enough to investigate.
Do you think you're actually what I was thinking when you were replying to the Raman effect and the Raman factor to Dimitri? Indeed, the fact that you have developed, let's call it an empirical way to assess in the femtosecond regime what is the equivalent Raman fraction from all the theoretical work. Could it be something that you could apply also to actually give a figure of merit for Raman effects in the femtosecond regime to all these materials where probably this issue that you mentioned about quality of a material, way in which it grows is a critical one, where also this could be interesting feedback for people fabricating.
I think that the way we did it until now is that we excited the soliton, we saw the continuum coming out, and then we tried to match it with the numerical simulations. This is probably a little bit too time consuming to do in general. But I think that in principle it shouldn't be that dramatic, because most crystals should have a quite low Raman effect, so you wouldn't guess it to be very high, and in that case it's not that critical. So in exploring new crystals, I would always just put something like 20% Raman in and see what happens and see if it matches. And that's a pretty good starting point. It just, I think, turned out the lithium niobate was a tricky one to nail down. But we have considered in the past building other dedicated kind of pump probe setup with femtosecond resolution that could actually determine the Raman coefficients of the crystals. but we never got around to having enough manpower to actually implement it, because it's a very technical thing.
Yeah.
And it's not something you can put into a high-profile publication. You might get, at the end of the day, you could get hundreds of citations because people use it as a reference for the Raman effect. But it is, at the end of the day, a very dusty piece of work. So the students are not usually super interested in that.
And now that, yes, I promised some questions on QPM, and that's what's coming, because it's, again, like a paradigm shift, what your
Yes.
aha moment wrote, in the sense that you can do, we all work with, most of the people would naturally think of working with quasi-phase matching to get interactions exactly phase matched, and instead of going off phase matching and then using new effects. So it's quite refreshing to have that point of view from outside. But at some point you actually, and I refer to the PRL with the tuning of dispersive way, you are using QPM, and now you're coming back again to QPM people and say, okay, wow, you can actually do something more with that based on those ideas. So my understanding is indeed you still get a kind of trade-off on approaching the phase matching regime,
Absolutely.
and instead still being far enough away from it, so that you can get still the equivalent cascading equivalent Kerr effect. So do you think there is more to build on that experiment and to be explored, or you essentially
yes, so there is an additional point here, as I mentioned also in responding to Dimitri's questions, that there is a lot of self-steepening going on in these crystals, and that is sort of the trade-off that you have with quasi-phase matching, is that as soon as you apply it, you increase self-steepening. And there is some work in the thesis just laying out that, and this is why we initially wanted to avoid it, because we couldn't see the point. Well, why would you want to use quasi-phase matching if all you got was much more self-steepening? We sort of destroyed your soliton at the end of the day. So it was only when we realized that we could actually sort of manipulate with these resonant radiation phase matching points with quasi-phase matching that we really thought that quasi-phase matching was relevant. The main attraction before that was basically control. Right? It gave us more control than we had before. It didn't give us more nonlinearity, but it gave us more control. So we let go of the nonlinear strength, but we gained more control. But we always tried to avoid this regime on purpose, because we knew that this regime is heavily influenced by self-steepening. So in previous work, we always avoided this like the plague, because we knew we would get in problems with self-steepening. And it actually also turns out that if you see the simulation behind this experiment, the soliton is not at all as clear as in the previous experiment. It's a much more dirty soliton, and you have to be a real hardcore soliton expert to see that it's actually a soliton. And this is because of self-steepening. And I have to add that this is also because we use a very short pump pulse. So here we have something like 60 femtosecond. If we use 100, 150, the self-steepening is less pronounced. So then we get a much more beautiful soliton. We have done other simulations after this where we see a much cleaner soliton and the same resonant radiation.
And my interpretation in terms of like practical trade-off is essentially that you have a trade-off between how much power you can put in that radiation wave, which is around 6%, I think, and actually the tunability and accessing that wavelength range, which is actually a tricky one. So do you think there is still scope for squeezing more power into there, or that's more or less
we have some ideas that we have not pursued yet, but it's basically about changing, using maybe a chirp grading, and then initially so we can sort of sweep the phase matching points. So we start maybe here, and then we sweep out here, and maybe we can generate like a continuous trail of resonant radiation. We don't know. We haven't even done the simulations yet, but these are some ideas that we have. It's not always that easy to do. I am optimistic though, because this is, in a normal case, you would rely on the soliton overlapping to see the photons coming there. But here we don't need to. It's just an down conversion. So that's why I think that can be cautiously optimistic about that effect.
That's cool, because it's exactly what I was about to ask you next. Essentially, what are the ways in which you can see using the degrees of freedom indeed of this aperiodic or maybe 2D if you deal with spatial aspect of QPM, and if you have, I know that again that will probably mean simulations even more complex and time consuming, but is it possible to think of some kind of inverse design of a QPM, knowing that now you have full control on matching with the simulation what you see in the experiment? Can you use that model to actually then work on an inverse design to tell you at that power in these conditions which aperiodic, and it could be something that maybe is more of a machine learning problem rather than actually intuitive.
Sure. No, I definitely think that this is possible, and that's also the strength of quasi-phase matching, that today the technology is so advanced that we can actually pick up the phone and call the company, and they can make us any phase mask. Not any, but within certain limits, they can give us a very strong control over what happens along the grading. But one thing that I think could be a showstopper is that this is a sort of, it's not a microscopic polling. It's not macroscopic, sort of in between. Mm-hmm. So you still need the cascading effect to sort of occur on a sort of macroscopic scale. Mm-hmm. So if you change too much the pitch along the way, then I'm not sure. You should think about how the soliton feels it. Mm-hmm. Somehow. That's my intuition. And there might be some cases that are sort of violating. The soliton will sort of try to adapt, I guess, if it's adiabatic at least. But there will be some issues there, because here we have a 30-40 micron pitch, and the coherence length is maybe a couple of microns, 3 microns. So you still have a lot of up and down conversions within a single grading. Mm-hmm. So it's there might be some issues there, whether you can really understand the quasi-phase matching as a global effect or a local effect. I'm not sure. But it would be really interesting to just start some simulations and see what is going on.
And I agree, of course, with what you say about the QPM, but I think you're also quite modest in not underlying the fact that having such a powerful model which couples so well to the experiment gives you a real advantage in trying to address that work. Absolutely. Which is, because it's not a purely abstract, there is a real coupling with what we do and what we see in the experiments. So definitely we'll be waiting for new ideas coming from you. I think, I don't know how, but yes, one last, well, maybe 2 questions. One is, my perception is maybe that now the interest, even if pulse compression was one of the first motivators 10 years back, in a way that part is exhausted, at least for the Chi2. The perspective is not that exciting anymore, at least you reach with the experiment where the limit is. And other aspects now, like supercontinuum generation with Chi2 nonlinearities and wave breaking effects even might be interesting ways to pursue, and also in terms of application. Is this a correct interpretation? Do you think that indeed is in the supercontinuum also that there is a lot to be done?
I definitely think that the large bandwidth that you can sort of generate with this process here is something that is quite remarkable. So of course that has an immediate application as a supercontinuum source, and we're trying to put this kind of thing into a waveguide right now, and that means that we can sort of compete with standard nonlinear fibers in that sense, and they are not that easy to pump at this wavelength and get this kind of bandwidth out of. So there is definitely an advantage of this kind of nonlinear processes. So I think that the soliton self-compression effect was an idea we pursued in the beginning because the community was mostly based on gas-filled hollow capillaries, and basically it only worked at 800 nanometers. Well, it also works at other wavelengths, but people that just hadn't really investigated it yet. And then there was typically a couple of millijoule of pulse energy limit, and then you could scale it up with different tricks. And so that was something that happened along the way when we were doing our work. So we sort of tried always to compete with it, and with our nonlinear crystals we can go to tens, if not hundreds of millijoules in principle. So that was always what we tried to work on, but now I think that there is this additional dimension of controlling the spectrum and the Chi2, intrinsic Chi2 in a supercontinuum is always a really, really wonderful feature to have, because if you want to lock the carrier envelope phase, you always externally try to do the second harmonic of the comb lines to see them and to lock them. But if they come out intrinsically from the waveguide, then you are in business already. So that alone is why the frequency comb community is getting more and more interested in Chi2 waveguides, and also micro-resonators. The same story, that they generate all these comb lines from spontaneously in the micro-resonator, but they never have enough bandwidth to actually lock. Only recently they discovered how to do that, but still they need to do external second harmonic to lock the carrier envelope phase.
And you mentioned moving again to waveguides to implement these concepts now. Do you see any challenges or opportunities, like let's call them? One, as I can tell, as a challenge is guiding in that wavelength regime and finding material. The opportunities maybe could be waveguide dispersion. Do you think that is actually also some tool which could be used?
I think it's something we haven't really investigated that much, because we did some work where we modeled some waveguides that had a lot of waveguide dispersion, but the challenge there is to get enough guidance bandwidth. So there were some advantages to just choosing a bigger waveguide. It's more power hungry, but it gives us overall what we need. It's nice to have some dispersion engineering for sure, and I think that lithium niobate is now getting mature enough to actually be used on a silicon platform. So you can actually grow thin layers of lithium niobate on top of the silicon wafer and actually manipulate that to get some good waveguides. And there you can really get really good waveguide dispersion that you can then exploit to get more control.
Okay, I said one question and I keep asking, but I have really one last, which is connected to your last slide. You had something also on nonlinear plasmonics.
Yes.
Can you tell us something about what is the direction, or maybe do you see already some application, or is it more, again, curiosity driven?
Well, that's a little bit adventure driven, I would have to say. It's basically because the question is, what do you expect will happen if you have a surface plasma polarity on a metal? So, and what is the response of a metal from a nonlinear point of view? And I came in with my nonlinear optics background, and the plasmonic community is not nonlinear at all. So they have a completely different way of seeing things. So there are some people in the community, including the work done in collaboration with Philip Russell, Andrea Marini, and they developed this Raman kind of response function, so that it just shows that the build-up of the nonlinear effect in a metal is very slow. So it takes something like 100 femtosecond to build up the hot electrons that are really generating the nonlinear effect, and then they decay over a picosecond time scale. So it takes a long time for the nonlinear effect to build up and die out again. So a lot of people in the plasmonic community, they are proposing to use 10 femtosecond Ti-sapphire lasers to pump to get the surface plasma polarity and get nonlinear effects. They will have large peak powers, but they will get a very small nonlinear response because the convolution between the field and the hot electrons will be vanishing small. So that was a takeaway that we got over 2-3 years of work. So now we have to figure out some way where we can actually exploit the nonlinear effects. So using maybe at least one easy thing is to use longer pulses to get more nonlinearity, right? So it sounds weird in this community that you need longer pulses to get more nonlinearity, but that's sort of a take-home message from that work that we did. And this is just on gold. So of course other metals behave more or less in a similar way. That's why we chose gold, but there might be some plasmonic materials that are more forgiving in that sense. Some oxides or other things that are also transparent in the mid-infrared, and that could be good candidates for nonlinear plasmonics, where you get low loss propagation and still get a decent nonlinearity.
Okay, I promise it was the last. And thank you very much for
Thank you.
all the work.
Thank you, Professor Gallo. Thank you to both of the opponents for the considerable work they have done in preparing for this defense. Thank you to the candidate. I would like to congratulate you. And as I explained earlier, I cannot congratulate you on obtaining the Dr. Technicus thesis, since there are procedures, as I already explained, that have to go on before we can do that. But what I can congratulate you on is completing the defense procedure today. And then, as was already announced, we will meet outside for a small reception and a drink and perhaps a toast. So see you outside.